Hey there, sleepless friends. Welcome back to Hafee Sleep. Whether you're tuning in from a bustling city where the lights never truly fade, or a quiet town where the stars are still visible, whether it's late night for you or the early hours of the morning, thank you for choosing to spend this time with me. Tonight, we're going on a journey together. Not just any journey, but the ultimate journey. We're going to travel trillions upon trillions of years into the future, to the very end of time itself. We'll be exploring how the entire universe, with all its galaxies, stars, and wonders, will meet its ultimate fate. Will it be a slow, cold fade into nothingness, a dramatic, fiery collapse, or something even stranger, born from the weirdness of quantum physics? It's a story of profound scale and quiet beauty, perfect for letting your mind wander as you drift off. So, get comfortable, close your eyes, and let your imagination soar across the cosmos. And if this journey into the deep future resonates with you, I'd be so grateful if you'd hit that subscribe button and give this video a like. It truly helps our little community of cosmic dreamers grow. I'm also genuinely curious, where in the world are you listening from, and what time is it for you? Let me know down in the comments. I love hearing from all of you. All right, let's dim the lights and begin our voyage to the end of everything. Imagine for a moment the most permanent thing you know. The ancient mountain range that has stubbornly resisted the wind and rain for millions of years. The deep ocean trench, forever hidden from the sun, a realm of timeless pressure and cold. The very continents upon which we live, drifting on a sea of molten rock at a pace so slow it defies human perception. We think of these things as eternal, as close to forever as our minds can comfortably grasp. But they are fleeting flashes in the dark, momentary sparks compared to the vast, yawning eternity that awaits the cosmos, the universe, our universe, with all its 100 billion galaxies, its trillions of trillion stars, its possibilities and wonders, was born in a single, spectacular moment of creation. And it, too, will have an end. The story of everything has a final chapter. It's a tale written not in ink, but in the fundamental laws of physics, a slow-motion destiny unfolding over timescales so immense they make the age of the universe itself seem like the blink of an eye. So, get comfortable. Let's dim the lights, look up at the imagined night sky, and venture forward, not for a few years or a few million years, but for trillions upon trillions of years into the future, to explore the ultimate fate of all that is, all that was, and all that ever will be. Our story of the end begins, perhaps paradoxically, with our current understanding of the beginning. The Big Bang wasn't an explosion in space. It was the explosive expansion of space itself. And a key player in this drama, a mysterious force discovered only relatively recently, is dark energy. Think of the Big Bang as giving the universe a mighty shove, sending all the galaxies flying apart from one another. For a long time, cosmologists thought the mutual gravitational pull of all the matter in the universe would act like a brake, slowly pulling on that expansion, perhaps slowing it down enough to one day stop it and reverse it. Gravity, after all, is the great attractor, the force that pulls things together. But in the late 1990s, observations of distant exploding stars revealed something shocking and profoundly strange. The expansion of the universe wasn't slowing down. It was speeding up. Something was actively pushing the galaxies apart, and that something was dubbed dark energy. It behaves like a kind of anti-gravity, an inherent property of the fabric of space itself that causes it to stretch at an ever-increasing rate. So we've set the stage with this bizarre, counterintuitive reality. The universe is not just expanding, but accelerating in its expansion, driven by this mysterious, ethereal force we call dark energy. We have made a video about the dark energy. If you haven't seen it yet, go and check that out. And the nature of this dark energy, specifically its density, is the master key that unlocks the universe's ultimate fate. Now, density is just a fancy word for how much of something is packed into a given space. Imagine a perfectly thin, uniform mist. That's dark energy. It's not clumpy like matter. It doesn't form into planets or stars or galaxies. It's a property of space itself. And as far as we can tell with our most powerful instruments, its density is constant. It's a very, very low density, but it's always the same. In every cubic centimeter of the vacuum of space, whether it's out in the void between galaxies or right here in this room, there is the same tiny, tiny amount of this repulsive energy. This is the crucial part. Because the density is constant, as the universe expands and creates more space, it automatically creates more dark energy. More space means more of the stuff that pushes space apart. It's a runaway feedback loop, a cosmic chain reaction of self-replication. The push doesn't just continue, it intensifies over time. It's like if you were baking that raisin bread we talked about earlier, and the dough had a magical property where the more it rose, the more leavening agent spontaneously appeared inside it, making it rise even faster. Gravity, the great attractor, works in the opposite way. As the universe expands, matter and radiation get diluted, spread thinner and thinner. Their gravitational pull weakens as the distances between them grow. So, in this cosmic tug-of-war, dark energy's team is getting stronger and more numerous, while gravity's team is getting weaker and more spread out. It's not even a contest in the long run. Dark energy wins. And its victory condition is a state of the universe known as the heat death, or the big freeze. Now, the name heat death is a bit misleading. It doesn't mean the universe will become hot. Quite the opposite. It comes from the 19th century idea of thermodynamics, the study of heat and energy. It describes the point where everything in the universe reaches the same temperature. There are no hot spots and no cold spots. No energy flows from one place to another because everything is uniform. It's the ultimate state of equilibrium, and it's the most boring, static, and lifeless state imaginable. It's not a dramatic, fiery explosion. It's a slow, quiet, and profound fading away. The universe, in this scenario, dies not with a bang, but with a whisper so faint and drawn out that it lasts for an eternity. So let's pull up a chair and watch this movie play out. Let's fast forward the cosmic clock, frame by agonizingly slow frame, and see what this victory for dark energy actually looks like. Our story begins not too far from now, just a few billion years into the future. From a human perspective, that's an unimaginably long time, but for the universe, it's just the next chapter. In this near future, our own galactic neighborhood is in for a major shakeup. Our beautiful spiral Milky Way galaxy is on a direct collision course with its even larger neighbor, the Andromeda Galaxy. Right now, Andromeda is hurtling towards us at about 110 kilometers per second. When we picture a galaxy collision, we might imagine a chaotic fireworks display of stars smashing into each other. But the reality is both more majestic and far less destructive. You see, galaxies are mostly empty space. If you could shrink a star down to the size of a marble, the next nearest star would be over 1,000 miles away. So when two galaxies merge, it's less like two cars crashing and more like two vast swarms of bees gently mingling together. The stars themselves will almost never collide. Instead, the immense gravitational forces of the two galaxies will pull and twist each other out of shape. Their beautiful spiral arms will be stretched into long, streaming tails of stars. They will swing past each other, then fall back together, and eventually, after a billion-year-long gravitational dance, they will settle down and merge into a single, giant, blob-like elliptical galaxy. Astronomers have already given this future hybrid a name, Milkomeda. For any beings living on a planet within this future galaxy, it would be the most spectacular light show in history. The night sky would be filled with a dizzying tapestry of new stars, glowing gas clouds, and the faint, shimmering trails of countless suns being flung into new orbits. It would be a time of cosmic construction, the building of a new island universe. But here's the ironic twist. While this dramatic local merger is happening, the larger universe beyond our local group of galaxies is undergoing the opposite process. It's flying apart. Dark energy is already at work. Those distant galaxies we see today, like the beautiful Pinwheel Galaxy or the majestic Sombrero Galaxy, are already beginning their long farewell. Their light, as it travels across the ever-widening gulf of space, is being stretched. We see this as redshift. The light waves are being lengthened, shifting towards the red end of the spectrum. As the expansion accelerates, this redshift will become more and more extreme. Now, let's jump further ahead. Let's travel to a time about 100 billion years from now. The universe is now about 8 times its current age. The merger that created Milkomeda is a distant, ancient memory, and the effects of dark energy have become utterly dominant. The expansion of space has accelerated to a ferocious pace. Remember, every galaxy not locked in a tight gravitational embrace with our own has been carried away by the stretching of space. And here's a mind-bending fact. Many of them are now moving away from us faster than the speed of light. Wait a minute. Doesn't that break the universe's ultimate speed limit? Not quite. Einstein's theory of relativity says that nothing can move through space faster than light. But space itself can expand at any speed it likes. There's no cosmic speed limit on the stretching of the fabric of space-time. Think of it like this. Imagine you're on a magic treadmill that can stretch. You're walking forward at your maximum speed of, say, 5 miles per hour. That's you moving through space. But if someone starts stretching the treadmill itself backwards at 10 miles per hour, even though you're walking forward as fast as you can, you're actually moving backwards relative to the ground at 5 miles per hour. Now imagine, the treadmill is stretching faster than any human can run. Anyone not on your little patch of treadmill would be carried away from you faster than they could ever hope to run back. That's what's happening to the galaxies. They are not engines propelling themselves through space faster than light. They are fixed points on a fabric that is stretching so fast that the distance between points increases at a rate greater than light could cover. The consequence of this is profound. The light from those distant galaxies can no longer reach us. The photons they emit, desperately traveling across the universe towards us, are trying to swim against a current of space that is flowing outward faster than they can move. It's a race they cannot win. They will never arrive. One by one, the galaxies will seem to freeze in place, their light redshifting into invisibility, and then they will wink out of view entirely, vanishing beyond a cosmic horizon. For an astronomer in the future Milkomeda galaxy, the observable universe will have shrunk dramatically. The night sky, which today is a glittering tapestry filled with the faint smudges of distant galaxies, will become almost perfectly, utterly black. The 100 billion galaxies will be gone. The evidence of the Big Bang, the cosmic microwave background radiation, the fading afterglow of creation, will have been stretched to wavelengths so long, so low energy, that it will be undetectable. All that will be left in the sky will be the stars of Milkomeda itself. Our galaxy will be an island in an endless, expanding blackness, a single, lonely ship on a dark ocean with no other ships in sight and no land on any horizon. We will be truly, utterly alone. But the story doesn't end there. It's just the end of the first act. The universe has removed all its distant scenery, but the local players are still on the stage. And these players, the stars, have their own life cycles to play out. So, let's look at the future of our own island universe, Milkomeda. Stars are not eternal. They are cosmic engines that run on nuclear fuel, and eventually they run out. Their lifespan depends entirely on their size. It's a classic case of the candle that burns twice as bright burns half as long. The most massive stars are the real drama queens of the universe. They live fast and die young. They pour through their immense supply of hydrogen fuel in just a few million years, ending their short, brilliant lives in catastrophic supernova explosions. Blasts so powerful they can, for a moment, outshine an entire galaxy. These explosions forge heavy elements like iron, gold, and uranium, and blast them out into space, seeding future generations of stars and planets. Then you have medium-sized stars like our own sun. It's been burning steadily for about 5 billion years, and has another 5 billion to go. It's the reliable, steady worker of the cosmos. When it runs out of hydrogen, it will swell into a red giant, swallowing the inner planets, probably including Earth, before eventually shedding its outer layers and collapsing down into a white dwarf, a super dense Earth-sized ember that will slowly cool over trillions of years. But the real long-distance champions are the smallest stars, the red dwarfs. These are the faint, cool, miserly stars that make up the vast majority of stars in our galaxy. They are so frugal with their fuel that they can shine for trillions of years, while the big stars have long since flamed out, and the suns of the world have faded to white dwarfs. The red dwarfs will still be chugging along, faintly glowing in the deepening cosmic night. However, even they are not immortal. Over the next several 100 trillion years, the process of star formation will first slow to a trickle and then stop completely. Why? The raw material is being used up and locked away. New stars are born from vast clouds of cold gas and dust. But this gas gets used up. Some of it gets fused into heavier elements inside stars. A lot more of it gets blown out of the galaxy altogether. You see, the galaxy is a dynamic place. When stars die in supernova, or when binary stars interact, they can kick each other with immense gravitational forces. These interactions act like a cosmic game of billiards, flinging stars, planets, and huge clouds of gas right out of the galaxy and into the intergalactic void. This gas, now out in the lonely darkness, is too hot and too diffuse to ever collapse back in and form new stars. It's lost forever. So, the last generation of stars will be born. They will flicker to life, burn for their allotted time, and die. And then, silence. No new stars will light the cosmic darkness. The era of star birth, which began with the first star hundreds of millions of years after the Big Bang, will be over. The universe will move into its next, even quieter phase, the degenerate era. The name sounds a bit judgmental, but it comes from a quantum mechanical term, degeneracy pressure. This is the force that keeps white dwarf stars and neutron stars from collapsing under their own gravity. It's not the heat of fusion holding them up anymore. It's the fundamental quantum resistance of electrons and neutrons being squeezed too close together. So, the degenerate era is the age of stellar corpses. Imagine the scene in Milkomeda now, perhaps a quadrillion, that's 1,000,000 billion years into the future. The galaxy is no longer a bright, sparkling spiral. It is a dark, ghostly relic. It is populated by the faint, cooling embers of dead stars, black dwarfs. A black dwarf is what a white dwarf becomes when it has radiated away all its heat over trillions of years. It is a cold, dark, Earth-sized crystal of carbon and oxygen floating in the absolute zero temperatures of space. It is the ghost of a star. There are also neutron stars, incredibly dense balls of neutrons just a dozen miles across but weighing more than our sun. A sugar cube-sized amount of neutron star material would weigh as much as a mountain. And then there are the black holes, the ultimate endpoints for gravity, regions of space where matter has been crushed to a point of infinite density, and from which not even light can escape. There is also the cold, dead remnants of planets. Frozen Earths, Jupiters, and Neptunes, their surfaces just a fraction of a degree above absolute zero. Their atmospheres frozen solid into ice on the ground. Many of these planets will have been flung from their dead solar systems during the gravitational chaos of the galaxy's old age, becoming rogue planets, wandering the eternal night alone, never again to orbit a star. This is a profoundly still and dark universe, but it is not quite completely static. There are still incredibly slow-motion events happening, occasionally over mind-boggling timescales. The subtle tug of gravity will cause two brown dwarfs, failed stars that never ignited, to collide, perhaps briefly sparking a faint new star in the darkness. But these will be the last, fleeting echoes of the brilliant stellar era. The main event of the degenerate era is far slower and more fundamental: the decay of matter itself. We are used to thinking of protons, the positively charged particles in the nucleus of every atom, as stable and permanent. But are they? Some of our best theories of particle physics, known as grand unified theories, suggest that the proton might not be forever. It might have a staggeringly long but finite half-life. The half-life is the time it takes for half of any large sample of a substance to decay. For protons, if they do decay, the predicted half-life is around 10 to power 34 to 10 to power 36 years. That is a number so vast it defies comprehension. Write down the number 1 and then follow it with 36 zeros. The current age of the universe is only 1.4 multiplied by 10 to power 10 years, a mere 14 billion years. We have never observed a proton decay, and experiments have shown that if it does happen, its half-life must be longer than the current age of the universe, which is why we haven't seen it. But if protons do decay, then even the seemingly permanent corpses of stars are not eternal. Picture a black dwarf, that cold, dark crystal of carbon. It is made of atoms, and atoms are made of protons, neutrons, and electrons. If protons decay, then over these immense timescales, the very matter of the black dwarf will disintegrate. The theory suggests a proton might decay into a positron, the antimatter counterpart of an electron, and lighter particles called pions, which would then decay into photons, pure energy. So a proton doesn't just vanish, it transforms into energy, but in doing so, the atom it was a part of falls apart. So over a period of perhaps 10 to power 40 years, an entire black dwarf star, once a brilliant sun, would slowly and silently sublimate away. It wouldn't explode. It would just evaporate. It would turn into a faint spray of light and subatomic particles. All the planets, the asteroids, the dust, every single solid object in the entire universe that is made of matter would suffer the same fate. The era of matter, of solidity, of objects would be over. The universe would be left with a thin, ever-cooling soup of leptons, like electrons and positrons, and photons. But wait, what about the black holes? They are still there, the darkest and most massive tombs in the universe. They seem like the ultimate end state, the final prisons for matter and energy. But thanks to the brilliant work of Stephen Hawking, we know that even black holes are not entirely black. They slowly evaporate through a process that is, frankly, magical. It's called Hawking radiation. This is a complex quantum effect that happens right at the edge of the black hole's event horizon. In the quantum vacuum, pairs of virtual particles constantly flicker into and out of existence. They are called virtual because they borrow energy from the vacuum for an incredibly brief moment, and then they annihilate each other and give the energy back. Usually this is undetectable, but if this particle-antiparticle pair pops into existence right at the event horizon of a black hole, something strange can happen. One particle might fall into the black hole, while the other escapes into space. The particle that escapes becomes real, carrying energy away from the black hole. To conserve energy, the particle that fell in must have negative energy, which effectively reduces the mass of the black hole. So black holes are not permanent. They slowly lose mass, emitting a faint glow of radiation. For a typical stellar mass black hole, this process is unbelievably slow. It would take about 10 to power 67 years for a black hole with the mass of our sun to evaporate completely. That is a 1 followed by 67 zeros. To put that in perspective, the current age of the universe is 10 to power 10 years. The supermassive black holes that lurk at the centers of galaxies, weighing millions or billions of times more than the sun, take even longer. A typical supermassive black hole might take 10 to power 100 years to evaporate. That number, 10 to power 100, is so large it has its own name, a Google year. It is a number larger than the number of atoms in the entire observable universe. Finally, after this almost endless duration, the black hole would evaporate away completely. In its final second, having been squeezed down to a tiny size, it would release a final burst of particles and radiation, a last tiny flash in the profound dark, and then it would be gone. Poof. And so, we arrive. The timeline is now truly beyond all human comprehension, perhaps 10 to power 100 years and beyond. All protons have decayed. All black holes have evaporated. What is left? A universe that is cold, dark, and almost perfectly empty. It is filled only with a desperately thin and ever-diluting sea of particles, photons that have been stretched to wavelengths larger than the current observable universe, their energy almost zero. Neutrinos that almost never interact with anything, and the leftover electrons and positrons from all that decay. These particles are so far apart that they might as well be alone in the universe. The temperature of this cosmos approaches absolute zero, the point where all motion stops. There is no energy flow, no structure, no change, no difference between one point in space and another. It is a state of maximum entropy. Entropy is a measure of disorder, and the universe has reached its final equilibrium state of perfect uniform disorder. There is no free energy left to do any work, to power any process, to create any structure or complexity. It is the end of history, the end of time in any meaningful sense. The universe has simply wound down. This is the heat death, a silent, static, eternal darkness. It is the ultimate victory of expansion over attraction, of emptiness over substance. It is a fate dictated by the strange, constant density of dark energy, a whisper from the vacuum that grows into a shout that echoes for an eternity before fading into the most profound silence imaginable. But is this the only possible ending? The fate of the universe hinges on the precise nature of dark energy. What if our current understanding is wrong? What if dark energy is not a constant force, but something that can change over time? This leads us to a second, much more dramatic family of theories. So, we've just taken a long, deep, and frankly sobering look at the universe's most likely fate, the heat death, a slow, cold, and quiet fading into nothingness over timescales so vast they numb the mind. It's a fate of isolation and stillness. But the universe, in its infinite mystery, might have other, far more dramatic endings in store. The heat death hinges on one critical assumption: that the dark energy pushing the universe apart is constant, that its repulsive strength remains unchanged forever. But what if it isn't? What if this force, this anti-gravity woven into the fabric of space itself, can change? Let's rewind our cosmic clock. Let's come back from that distant, cold future to our present, or at least to a time where the universe still looks somewhat familiar, with galaxies glittering in the night sky. We're going to consider a different possibility, a scenario where dark energy doesn't just have a constant, gentle push. What if it's something else? What if it's a force that grows stronger over time? This isn't just a wild guess. It's a legitimate question that physicists ask based on some of their theories about what dark energy could be. And if the answer is yes, if dark energy can intensify, then the fate of the cosmos shifts from a slow freeze to a sudden and violent shredding. This is the second major theory of the end, and it has a name that perfectly captures its essence: the Big Rip. The Big Rip is a story that is short, brutal, and utterly terrifying. It makes the heat death look almost peaceful by comparison. In the heat death, the universe dies of old age and exhaustion. In the Big Rip, the universe is torn apart in its prime. It's the difference between a candle gently burning out and a candle being violently snuffed out by a hurricane. To understand how this could happen, we need to think about the different forces that hold reality together. Our universe is built on a hierarchy of structures, each bound by a specific force, each force with a different strength. At the largest scales, we have galaxy clusters bound together by the relentless pull of gravity. Then, within those clusters, individual galaxies are also held together by gravity, the combined gravity of all their stars, gas, and dark matter. Zoom in further, and solar systems are held in place by the gravity of their central star. Our Earth is held in its orbit by the Sun's gravity, and our Moon is held to us by Earth's gravity. Zoom in even more, and we get to the scale of planets, rocks, and people. These are held together not by gravity, but by electromagnetism, the chemical bonds between atoms that form molecules, cells, tissues, and entire worlds. Gravity is incredibly weak at this scale. The electromagnetic force that holds your body together is stronger than the Earth's entire gravitational pull on you. And then, at the very smallest scales, inside the nucleus of every atom, the strong nuclear force holds protons and neutrons together with a strength that makes electromagnetism look feeble. In our everyday lives, and in the heat death scenario, this hierarchy of forces is stable. Gravity rules the large scales, Electromagnetism rules the human scale, and the strong force rules the atomic scale. They don't interfere with each other. But the Big Rip scenario imagines a dark energy so potent, so ferociously strong, that it doesn't just overwhelm gravity, it eventually overwhelms every single one of these forces, one by one, from the largest down to the smallest. It's a cosmic tide that starts by pulling islands apart and ends by pulling apart the very molecules of the sand on the beach. The story begins in a way that looks eerily similar to the early stages of the heat death. Dark energy is pushing the galaxies apart. But in this story, the push is much, much stronger. Because the dark energy's density is increasing, its repulsive power grows as the universe expands. It's not a constant gentle shove. It's a foot pressing down harder and harder on the accelerator. The first structures to feel the strain are the largest gravitationally bound ones, galaxy clusters. These are vast families of hundreds or even thousands of galaxies, all orbiting a common center of gravity. Their bonds are powerful, but in the face of an exponentially strengthening dark energy, they are the first to snap. The space between the galaxies within a cluster begins to expand so violently that it overcomes their mutual gravitational attraction. The cluster is literally ripped apart, its member galaxies flung away from each other into the ever-widening void. This would happen relatively quickly on a cosmic timescale, perhaps within a few tens of billions of years from now. Next, the rip comes for the individual galaxies themselves. A galaxy like our Milky Way is a gravitationally bound system. The Sun and all the hundreds of billions of other stars orbit the galactic center, held in place by the immense gravity of the supermassive black hole at the core, and more importantly, by the vast halo of dark matter that surrounds the galaxy. But the accelerating expansion of space, now growing in ferocity, would eventually overcome even this. The stars would be pulled away from each other. The beautiful spiral arms would be stretched and then dissolved. The galaxy would be dismantled, its stars becoming isolated beacons, each one alone in an incomprehensibly vast and growing darkness. Imagine a swarm of gnats, held together in a cloud by their subtle interactions with each other. Now, imagine a hurricane wind blowing through the swarm, scattering every gnat to a different corner of the sky. That's what happens to a galaxy in the Big Rip. But the rip is just getting started. Its power is growing exponentially. The next victims are solar systems. Take our own. The Earth is held in its orbit by the Sun's gravity. That gravitational bond is incredibly strong. It's kept us in a stable orbit for over 4 billion years. But in the Big Rip scenario, the expansion of space itself, right here in our solar system, would become so violent that it would overcome the Sun's gravity. The space between the Sun and the planets would literally stretch faster than gravity could pull them together. The planets would be ripped from their orbits and hurled away into the interstellar void. The Earth would be torn away from the Sun. The Moon would be torn away from the Earth. They would all become rogue planets and moons, flying alone through the blackness, their familiar dance forever broken. There would be no more sunrises, no more years, no more seasons, just a perpetual freezing and accelerating flight into nothingness. And it gets worse. The force continues to intensify. Now it comes for the stars and planets themselves. A star is a delicate balance. For most of its life, it's in a state of equilibrium called hydrostatic equilibrium. The inward crush of its own immense gravity is perfectly balanced by the outward pressure from the nuclear fusion raging in its core. This balance keeps the star stable in size. But the Big Rip introduces a new external force. The expansion of space itself, now raging with unimaginable power, would provide an outward push that adds to the fusion pressure. The balance is shattered. The star's gravity is no longer strong enough to hold it together against the combined push of fusion and the expansion of the universe. The star is literally torn apart. Its plasma, its gas, its very substance is pulled outward and scattered into a diffuse cloud. The same fate befalls planets. The gravitational force that holds a planet together, that keeps it a sphere instead of a cloud of dust, is overcome. A planet like Earth would simply fly apart. Mountains would not just crumble, they would be leveled as the space between their molecules expands violently. Continents would be pulled away from each other. The entire planet would be disassembled into a cloud of rocks, then dust, then individual molecules, in a matter of moments. Now we are in the final, horrifying moments. The rip has destroyed all large-scale structure. There are no galaxies, no stars, no planets. There is only a diffuse, expanding cloud of particles. But the dark energy is still getting stronger. The expansion rate is hurtling towards infinity. Now, the rip reaches down to the very fabric of matter itself. It attacks the forces that hold us together. First, it overcomes the electromagnetic force. This is the force that holds atoms together to form molecules. It's the force behind every chemical bond. It's the force that holds the cells of your body together. When the expansion of space overcomes this force, every molecule is torn apart. Your body, any hypothetical observer, would not be crushed or vaporized in a traditional sense. You would simply disintegrate. The atoms that make up your molecules would be pulled away from each other with such force that every bond would snap simultaneously. You would dissociate into a diffuse cloud of individual atoms spreading out into the void. But the rip is not finished. Its power is now almost infinite. It reaches into the atom itself. It attacks the strong nuclear force. This is the mightiest force in nature, the glue that holds the nucleus of an atom together. Protons and neutrons are bound together with incredible strength in the atom's core. But in the face of the Big Rip's final, cataclysmic moments, even this force fails. The nuclei of every atom are torn apart. Atoms cease to exist. They are shredded into their constituent particles. A soup of quarks and gluons, the fundamental building blocks of matter, now scattered and isolated. And then, in the last fraction of a second, the expansion rate becomes truly infinite. What happens now is beyond our current physics. We believe that space-time itself, the very stage upon which the universe plays out, would be ripped apart. The fabric of reality would be shredded. The concepts of here and there, of now and then, would cease to have any meaning. It would be a true singularity, a discontinuity, not just in the history of the universe, but in the laws of physics themselves. The universe would end not with a whimper, but with a literal, violent tear in the fabric of existence. The entire timeline of the Big Rip, from the first tearing of galaxy clusters to the final shredding of space-time, could happen remarkably quickly. Depending on how fast the dark energy intensifies, it could all be over in a few tens of billions of years, or even less. It's a sudden, violent, and definitive end. Now, after that terrifying journey, it's important to take a breath and offer a bit of reassurance. As dramatic and frightening as the Big Rip is, most of the current astronomical evidence we have suggests that it is not our fate. Our measurements of dark energy, while still filled with uncertainty, point towards it being constant, or at least not growing in the violent way required for a big rip. The heat death remains the reigning champion for the most likely end of the universe. The big rip is a possibility, a dramatic and fascinating one that lives on the more extreme edges of our theories, a reminder of how strange and powerful the forces governing our cosmos truly are. It's a testament to the fact that the universe, for all its apparent order, is capable of endings of unimaginable violence. After the chilling emptiness of the heat death and the terrifying violence of the big rip, we might be yearning for a different kind of ending, something with a sense of closure, perhaps even a hint of poetry, a story that feels less like a slow fading away or a sudden tearing apart, and more like a story with a final dramatic climax. Well, the universe might have had such a story in mind, at least in its original draft. Before the shocking discovery of dark energy and the accelerating expansion in the late 1990s, this was the ending most scientists believed in. It's a classic, almost mythical narrative, the Big Crunch. It's the idea that the universe, after its spectacular birth in the Big Bang, might one day reverse its course and fall back in on itself. To imagine this, we have to mentally erase dark energy from the cosmic equation. We have to go back to a simpler model of the universe, one where the only major players are the initial momentum of the Big Bang and the relentless, patient pull of gravity. In this version of events, the fate of the cosmos is a simple tug-of-war between these two forces. The Big Bang provides the outward thrust, the explosive expansion. Gravity provides the inward pull, the brake. The ultimate question was, which one is stronger? Is there enough stuff in the universe, enough matter and energy for gravity to eventually win? The Big Crunch scenario is the story of gravity's ultimate victory. It's the story of the Big Bang played in reverse. It begins not with a bang, but with a slow, almost imperceptible sigh. The expansion of the universe, which has been slowing down since the very beginning under gravity's influence, continues to decelerate. The galaxies, which are all flying apart from each other, begin to slow their retreat. It's like throwing a ball straight up into the air. For a while it climbs, but gravity is constantly slowing it down until it reaches a momentary pause at the apex of its flight, and then it begins to fall back to Earth. In the Big Crunch, the entire universe reaches that apex. The expansion slows, and finally stops. There is a moment of cosmic stillness, and then the long fall begins. The contraction starts. It's gentle at first. Galaxies that were moving apart begin to approach each other. The redshift of distant galaxies, which was the telltale sign of expansion, would gradually decrease to zero, and then turn into a blue shift as they start moving towards us. The universe is beginning to shrink. As the contraction continues, subtle changes begin to occur in the cosmos. Remember the cosmic microwave background radiation? That faint cold afterglow of the Big Bang that permeates all of space, currently at a frigid 270 degrees Celsius? As the universe contracts, this radiation gets compressed. The wavelengths of these photons are shortened, and in physics, shorter wavelength light is more energetic, which means it's hotter. So the background temperature of the universe, which has been dropping for billions of years, begins to rise. The universe starts to warm up. At first, this warming is insignificant, but as the contraction continues, it accelerates. Gravity is a runaway process. The closer things get, the stronger the gravitational pull becomes, which pulls them even closer together, making the pull stronger still. The contraction picks up speed. The background temperature of the universe climbs from its deep freeze to the temperature of a cold room, then to room temperature, then to the temperature of a hot summer day. The night sky, which is currently a black canvas dotted with points of light, would begin to change. It would no longer be perfectly black. It would have a faint, uniform, warm glow. It would be as if someone were very slowly turning up a dimmer switch on a giant, all-encompassing light bulb. The contraction is now becoming serious. The galaxies, once isolated island universes separated by millions of light years of void, are now drawing closer together. Their mutual gravitational attraction begins to warp their paths. They start to collide. But this isn't the graceful billion-year-long dance of the Milky Way and Andromeda. This is a chaotic, violent traffic jam on a cosmic scale. With space itself shrinking, galaxies are being forced into closer and closer quarters. They slam into each other, their gravitational fields tearing each other apart. Stars are flung from their galaxies like sparks from a grinding wheel. Solar systems are disrupted and destroyed in the chaos, and all the while the background temperature is soaring. It passes the boiling point of water, then the melting point of iron, then thousands of degrees, then millions. The sky is no longer a gentle glow. It is a blazing, uniform furnace. The universe is now hotter than the surfaces of most stars. This has a catastrophic effect on the stars themselves. A star is a carefully balanced system, but its existence depends on a cold surrounding space to radiate its heat into. Now, the environment around it is hotter than it is. Stars can no longer shed their heat. They begin to cook. Their outer layers are heated by the ambient radiation of the universe itself. Nuclear fusion processes are disrupted. Stars are vaporized, their structures dissolving back into the hot, dense plasma from which they formed. The universe is reverting to its infancy. The temperature is now in the billions of degrees. Atoms, which only formed hundreds of thousands of years after the Big Bang, when the universe had cooled sufficiently, cannot exist in this inferno. The intense radiation smashes them apart as soon as they try to form. Electrons are ripped away from atomic nuclei. The universe is a shrinking, thickening soup of atomic nuclei and free electrons, a plasma, the primordial state of matter. The contraction is now terrifyingly fast. The universe, once larger than our minds can comprehend, is now smaller than the current observable universe, then smaller than a galaxy, then smaller than a solar system. All the matter and energy that ever existed is being compressed into an ever smaller volume. The temperature and density are soaring towards infinity. The laws of physics as we know them begin to break down. Time and space themselves become distorted and warped. Finally, the entire universe, every star, every planet, every molecule, every atom, every moment of history, every memory, every thought that was ever thought, is crushed into a single point, a singularity, a point of infinite density, infinite temperature, and infinite curvature of space-time. It is the ultimate opposite of the Big Bang, the Big Crunch. It is the end of the line, the ultimate collapse. But is it? Could it also be a beginning? This is where the theory ventures from physics into the realm of metaphysics and poetry. Some cosmological models, particularly those in loop quantum gravity, suggest that such a singularity might not be a true end. The incredible repulsive forces generated at such insane densities could cause a quantum bounce. Instead of collapsing into nothingness, the universe might rebound. The Big Crunch singularity would become the seed for a new Big Bang. The universe would be reborn, expanding outwards once again, perhaps with different fundamental constants and physical laws. This is the idea of the cyclical universe, or the phoenix universe. It dies in the fire of the Big Crunch, and from its own ashes, it is reborn in a new Big Bang. It's a profoundly appealing and beautiful idea. It suggests an eternal cycle of birth, death, and rebirth, echoing the cycles we see in nature on Earth. It offers a kind of immortality to the cosmos, if not to any of the structures within it. Unfortunately, and perhaps sadly, the evidence we have today suggests this is not our universe's story. The discovery of the accelerating expansion in 1998 was the death knell for the classic Big Crunch model. It told us that the expansion isn't slowing down enough for gravity to ever reverse it. There simply isn't enough matter and energy in the universe to win the tug of war against dark energy. The ball we threw up at the beginning of time doesn't have enough mass in the universe to pull it back down. It's going to keep going forever. The phoenix will not rise from these ashes. The cyclical universe, for all its poetic beauty, appears to be a road not taken by our particular cosmos. Yet, it remains a powerful and important part of the conversation. It reminds us that the universe's fate wasn't a foregone conclusion. It could have been different, and in some other universe, perhaps with different laws or different initial conditions, that great cosmic cycle of death and rebirth might be playing out on an eternal loop. For our universe, however, the path seems to lead toward colder and lonelier ends. After exploring the grand slow-motion finales dictated by gravity and dark energy, we now venture into the quantum shadows, into the realm of the deeply strange and the profoundly spooky. Here, the universe's end might not come from a gradual running down of the clock or a dramatic cosmic tug of war, but from a sudden, random, and fundamental rewrite of the rules of reality itself. This isn't an ending you see coming from a billion light years away. This is an ending that could, in theory, begin at any moment, anywhere, and rewrite existence at the speed of light. This is the most speculative and, in some ways, the most terrifying possibility of all: vacuum decay. To even begin to understand this, we have to talk about nothing, but not just any nothing. We have to talk about the vacuum of space. We often think of a vacuum as pure emptiness, a true void. But quantum physics tells us that the vacuum is anything but empty. It's a seething, bubbling, frothing sea of potentiality. It's alive with what we call quantum fluctuations. Pairs of virtual particles and antiparticles constantly pop into existence, borrowing energy from the vacuum for an unimaginably brief moment, before annihilating each other and paying the energy back. This isn't just theoretical. We can measure the effects of this frenzy. It's the reason your radio can pick up static from seemingly nowhere. The vacuum is, in fact, the most complex thing we know. And at the heart of this bustling quantum vacuum lies something absolutely fundamental to our existence: the Higgs field. Now, a field in physics isn't like a farmer's field. Think of it more like an invisible fluid, an ocean that fills all of space, everywhere, equally. You can't see it, you can't touch it, but its effects are everywhere. The Higgs field is a very special kind of fluid. Its interaction with other particles is what gives them mass. Imagine wading through a swimming pool filled not with water, but with a kind of cosmic molasses. The harder it is to move through this molasses, the more mass you have. A photon, a particle of light, zips through this molasses without interacting with it at all. It's massless. An electron sloshes through it with a little difficulty. It has a tiny mass. A top quark, a fundamental particle, is like a person wearing lead boots in this molasses. It struggles immensely to move, and thus has a very large mass. This isn't a perfect analogy, but it gives you an idea. The Higgs field is the molasses, and the resistance particles experience moving through it is what we perceive as mass. Without the Higgs field, nothing would have mass, atoms couldn't form, and the universe as we know it would be impossible. Now, here's where the story gets precarious. The current state of this all-important Higgs field, the value of its molasses-like thickness that gives particles their mass, might not be the most stable state it can be in. Physicists call our current state a false vacuum. This is a concept that is best understood with a metaphor. Imagine a vast rolling landscape of hills and valleys. Now imagine a ball sitting in a small, cozy valley. It looks stable. It feels stable. If you give it a small nudge, it'll just rock back and forth and settle right back to the bottom. This is our universe. The ball is the value of the Higgs field, and the small valley is the state it's in right now. It seems perfectly stable. But what if this small valley isn't the lowest point in the entire landscape? What if it's just a little dip on the side of a much larger hill, and at the bottom of that hill is a much, much deeper valley? That deeper valley represents the true vacuum, the absolute lowest energy state the Higgs field could possibly be in. Our universe is sitting in that higher valley, the false vacuum. It's stable for now, but it's not truly stable. It's metastable. It's like a pencil balanced on its point. It can stay like that for a very long time, but eventually it will fall. How could it fall? Through a bizarre quantum phenomenon called tunneling. In the everyday world, if you want a ball to get from one valley to another, you have to give it enough energy to roll up and over the hill between them. But in the quantum world, particles and fields don't always play by those rules. There's a chance, a very small, probabilistic chance, that the ball could simply disappear from one valley and reappear in the other without ever going over the top. It's as if it dug a tunnel straight through the hill. This isn't science fiction. It's a well-understood process that explains how radioactive atoms decay and how the sun shines. Quantum tunneling is real. So apply this to the Higgs field. At some random point in space, at some random time, a quantum fluctuation could cause the Higgs field to tunnel from its current, seemingly stable state, the false vacuum, down to its true, lowest energy state, the true vacuum. This wouldn't be a physical explosion. It would be a phase transition, like water suddenly flash freezing into ice across the entire ocean. But this would be a phase transition of reality itself. The moment this tunneling event happens, a bubble of true vacuum is born. This isn't a bubble of air. It's a bubble of space where the fundamental laws of physics are different. The properties of this new vacuum are a mystery. The Higgs field would have a new value. This could mean that the masses of all fundamental particles are different. The electron might become heavier than a proton. The quarks that make up protons and neutrons might have their bonds altered. The constants that govern the strength of forces like electromagnetism and the strong nuclear force could be completely rewritten. In this new state, the rules of chemistry and atomic physics as we know them would be null and void. Atoms, as we define them, would likely be impossible. Molecules couldn't form. The very structure of matter would be obliterated. Anything made of atoms, planets, stars, people, would instantly and irrevocably cease to exist in any recognizable form. They would be transmuted into something else entirely, something that likely could not support any form of life or complexity. It would be an ontological catastrophe, a change in the very nature of being. And the worst part? This bubble would expand, and it would expand at the speed of light. The wall of this bubble would be a sphere of fundamental change, a wave of new physics washing across the universe. From the outside, you wouldn't see it coming. There's no signal, no warning that can travel faster than light. The moment you see the wall of the bubble, it is already upon you. 1 nanosecond you exist in a universe with atoms, stars, and physical laws you understand. The next nanosecond, you and everything you've ever known are gone, transformed into a new state of existence governed by alien rules. It would be instant, painless, and total. The entire observable universe would eventually be converted into this new, true vacuum state. It's a terrifying thought, that the universe might be fundamentally unstable, and that a random quantum event could erase the delicate balance that makes our existence possible. It means the laws of physics are not necessarily eternal and immutable. They could be local and temporary conditions, a happy accident that could be undone at any moment. Now, before you look at the world outside with newfound anxiety, let's breathe a sigh of relief. The key word in all of this is metastable. Our valley, our false vacuum, appears to be incredibly stable. The energy hill separating us from the true vacuum is, according to our best measurements, enormously high and wide. The probability of a tunneling event happening in any given cubic centimeter of space in any given second is astronomically, mind-bogglingly small. So small that the expected time for such an event to occur somewhere in the observable universe is far, far longer than the current age of the universe. It likely hasn't happened once in 13.8 billion years. The chance of it happening in our corner of the cosmos during the entire future lifespan of humanity is effectively zero. But, and there's always a but in cosmology, on the infinite timescales we've been discussing, like the googles of years in the heat-death scenario, the improbable becomes inevitable. If the universe truly is metastable, and if it continues existing forever in an otherwise empty void, then given enough time, a quantum fluctuation will eventually trigger vacuum decay. It could happen a Google year from now, in the cold, dark depths of the universe degenerate era. A single random quantum event in the depths of empty space could spell the end, not with a freeze or a rip, but with a silent, light-speed rewrite of everything, bringing a sudden and final end to the eternal silence. It's a sobering reminder that the universe's deepest workings are strange beyond belief, and that our cozy, stable existence is perhaps more fragile and precious than we could ever imagine. So, we've journeyed through the 4 great pillars of cosmic finality: the slow freeze, the violent rip, the fiery crunch, and the silent quantum rewrite. But the human imagination, and indeed the frontiers of theoretical physics, don't stop there. The universe is a place of infinite possibility, and its potential endings are just as myriad. Some of these ideas are extensions of the theories we've already discussed, while others come from entirely different branches of thought, like the wild and wonderful idea of the multiverse. These are the exotic theories, the far-out possibilities that live on the very edge of science, where hard calculation meets profound speculation. Let's start with the idea of a universe-to-universe collision. This springs from the concept of the multiverse. The multiverse is a collective term for a bunch of theories that suggest our universe might not be the only one. It might be one bubble in a grand cosmic foam, one page in an infinite book of realities. One popular version of this is the theory of eternal inflation. It suggests that the Big Bang wasn't a one-time event, but a localized event within a much larger, eternally inflating megaverse. In this megaverse, the fabric of space is expanding at an incredible rate. But every now and then, in a random location, this inflation stops, and that patch of space becomes a stable bubble universe with its own Big Bang and its own set of physical laws. Our universe is one such bubble. Now, imagine these bubbles floating in the inflating foam. They might be moving. They might even be expanding themselves. What happens if two of these bubbles collide? If our universe were to collide with another bubble universe, the consequences would be as catastrophic and as instantaneous as the vacuum decay we just discussed. The reason is simple. The other universe would almost certainly have different fundamental physics. The value of its Higgs field would be different. The strength of its forces would be different. The very constants of nature, like the speed of light or the gravitational constant, might not be constant across the boundary between the two universes. The moment the two bubbles touched, it would create a boundary zone, a cosmic shore where two entirely different sets of physical laws met. This would not be a peaceful merger. It would be a cataclysm of unimaginable proportions. The laws of physics that govern our matter would break down at the point of contact. It would be like two grids with completely different patterns trying to mesh together. They simply can't. The collision would likely send a shock wave through our universe, a wall of fundamental change not unlike the wall of the true vacuum bubble, propagating at the speed of light. As it passed, it would rewrite reality, probably rendering life, chemistry, and even atomic structure impossible. We wouldn't see it coming. One moment, everything is normal. The next, a wave of otherness is upon us, and existence as we know it is erased. It's a terrifying and thrilling thought, but there's a twist that makes it even more so. Some theories suggest that the evidence for such a collision might already be etched into the oldest light in the universe, the cosmic microwave background. Some cosmologists have even scoured the CMB maps, looking for strange circular patterns or anomalous cold spots that could be the cosmic bruise from a long-ago collision with another universe. So far, nothing conclusive has been found. But the search itself shows how seriously these ideas are taken. Now, let's swing our perspective all the way back to the heat death. We left it as the final, eternal, silent state of maximum entropy, a frozen, dead universe where nothing ever happens again. But is that truly the end? Quantum mechanics, the theory of the very small, might have a say in this. Quantum mechanics is built on probability. Nothing is ever certain. Everything is a matter of chance. And given enough time, and I mean enough time in the most extreme sense of the word, even the most outrageously improbable events become not just possible, but inevitable. This leads us to perhaps the most bizarre and mind-bending idea of all, quantum resurrection. Or, more formally, the idea of Boltzmann brains and Poincaré recurrence. It's a thought experiment that emerges from the marriage of thermodynamics and quantum mechanics in a universe that lasts forever. The principle is simple. In a state of maximum entropy and random quantum fluctuations, anything that can happen will happen. Eventually, given an infinite amount of time, the random jostling of particles, even in a universe that is nearly a perfect vacuum and almost at absolute zero, will by sheer, blind, incredible chance assemble itself into any possible configuration. This includes the configuration of an entire new Big Bang. Think of it like this. Imagine you have a box filled with the Scrabble tiles for the complete works of Shakespeare. If you shake the box at random for an infinite amount of time, the tiles will, at some point, accidentally fall out onto the floor and spell out the entire text of Hamlet perfectly, without a single error. The probability of this happening is so small, it's effectively zero for any finite amount of time. But infinity is a long time. In an infinite timeline, it becomes a certainty. Now, apply that to the universe. In the quadrillions of years of the Dark Era, the universe is a vast, nearly empty box, but it's not completely empty. It's filled with that thin soup of photons, electrons, positrons, and other particles, all randomly fluctuating. Over an immense duration, these particles will randomly quantum tunnel into new arrangements. The chance of them spontaneously forming, say, a perfect replica of the planet Earth with you on it, reading this exact sentence, is absurdly, incomprehensibly tiny. A self-aware entity that forms from such a random fluctuation is called a Boltzmann brain, and it's a major philosophical puzzle for cosmologists. But an even more spectacular fluctuation is possible. All the particles in the dead universe could, by a random quantum fluctuation, suddenly find themselves arranged exactly as they were at the moment of the Big Bang. A new singularity could just pop into existence from the quantum foam of the old, dead universe. This wouldn't be a bounce from a crunch. It would be a spontaneous rebirth from nothing but random chance and infinite time. A new universe would then explode into being, with a new history, new laws of physics perhaps, and a new cycle of life and death. This process is related to a mathematical concept called Poincaré recurrence, which suggests that given enough time, a system will eventually return to a state arbitrarily close to its initial state. The timescales for this are not just astronomical, they are trans-astronomical. They are numbers so vast they defy notation. We're talking about times like 10 raised to the power of 10 raised to the power of 10 raised to the power of 56. Try to type that into a calculator. You can't. It's a number so large that if you tried to write it out as a decimal, using a zero on each Planck-sized volume in the entire observable universe, you still wouldn't have enough space. It is, for all practical purposes, infinite, but it is not actually infinite. And in that slim difference between practically infinite and actually infinite, hope for a cyclical cosmos born from randomness somehow persists. It's a fascinating, almost poetic thought, that even in the absolute coldest, darkest, most empty and desolate future imaginable, the seeds of a new beginning might lie dormant, that the universe, in its ultimate death, might hold the potential for an infinite number of rebirths, each one a random throw of the quantum dice. It suggests a cosmos that is ultimately eternal, not in its structures, but in its potential for renewal, even if that renewal is just a fleeting, random accident in an eternity of silence. It means the story of the universe might not have a final period at the end. It might have an ellipsis, followed by another story and another and another, each one unknown, each one separated from the last by an ocean of time so deep and so dark that it makes the current age of the universe seem like a single fleeting spark in an endless night. So, which of these ends is our fate? The evidence, as it stands today, points most strongly to the heat death, the long, slow fade into darkness. The measured value of dark energy seems to be constant and just right for continued acceleration without a big rip. The density of matter is too low for a big crunch. Vacuum decay remains a terrifying but unproven possibility. The heat death seems to be our most likely destination. It's a profoundly humbling and seemingly bleak picture, a universe destined for emptiness, silence, and cold. But is it truly bleak? To think so is to view it through a human lens, with our brief lifespans and our desire for narrative and meaning. The universe is not cruel or kind or wasteful or bleak. It simply is. It follows the laws of physics with utter impartiality. The fact that it gave rise to us, conscious beings who can look out, trace its history, and ponder its immense future, is a beautiful and remarkable thing. We are a fleeting spark of light and mind in the long, dark childhood of the universe. The cosmos was able to know itself for a little while through us. The story of the universe's end is not a tragedy. It is an epic. It is the final, necessary chapter in the story that began with a flash of light. It is the ultimate demonstration that everything, on a long enough timeline, must change and must end. And in that ending, there's a strange, cold, and magnificent kind of peace. The peace of equilibrium. The peace of silence after the last note of the cosmic symphony has faded away, leaving only the endless, empty concert hall of space-time. So, the next time you look up at the night sky, remember, you are not looking at a static, eternal picture. You are looking at a single frame in a movie trillions of years long. You are witnessing a moment of glorious, vibrant activity in the brief springtime of the cosmos. The stars are shining now, the galaxies are spinning now, and we are here now to see it. And that, in the face of the incomprehensible eons to come, makes this present moment and our ability to contemplate the abyss infinitely precious. Good night and enjoy a deep sleep.